All right. Thank you, George. Welcome, everybody. So, George talked about the bad old days when we worked on things for years and years and years before, we released them, and how now we've moved to a time where we're able to deliver things more quickly, slice them into finer, finer slices. So, I'm going to talk today about something I've been thinking about for years and years. When it comes to the Java language, you don't get a second chance. You don't get to put a bad feature in and say, oh, that was a mistake. And so we think very carefully about what features we want to put into the language. And I've been thinking for a long time about a number of features where, well, we could do it this way, but that would be really disappointing. It feels like there's a better way to do it in there somewhere, but we didn't quite know what it was. And so I spent a lot of time looking at what other languages did, in this area. And we feel like we've come to a point now where we have a pretty good idea of which way we want to go with this. And so what I want to talk about today is an approach and a set of features that are designed not to be used by themselves as a way to write better programs, but as a mechanism for making the language more growable and more extensible so that when we add a feature, user code can interact with that feature and extend it sort of on their own. So if you look at programming languages, every programming language picks a place where it wants to put the boundary between what's the language's area and concern and area of control and what is user code allowed to do. And different programming languages pick different ways to set this barrier. For example, in the Lua language, you can't create new types. There are 8 or 9 built-in types, number, lambda, map, sequence, C pointer, et cetera, and you don't get to abstract over types. You get to use the types that they have. Whereas other languages, kind of at the other end of the extreme, like Ruby, let you tinker with the mechanics of method dispatch. Method dispatch is just like ordinary behavior that uses maps of things, and you can put your own stuff in those maps and change the way the language does method dispatch. And one of these is not better than the other. These are just different philosophical choices about how the language is intended to be used. And Java is somewhere in the middle, at least on these examples. So you can write new types in Java. We call them classes and interfaces. And they look a lot like the built-in types, like string and object, except for those pesky 8 types like int, float, double, which are built in and are magic. And similarly, like new operations, you can write new operations. These are called methods, and they look a lot like the methods on built-in types, like string.length, except for those pesky operations that have special symbolic names like, plus and times. Like most languages, the syntax of the Java language is fixed. There's no language feature that lets you change the syntax of the language. But no matter where you choose to put this boundary, as a language designer, there's always going to be a seam. There's always going to be a language space, user space seam. And language designers, as part of their design philosophy, choose where they're going to put the seams and how obvious they're going to be. An example I ran across that was kind of amusing was the first language I programmed in was PDP-11 Basic in like 1977. And one of the things that, and it had a number of built-in functions like sine and cosine and such. And one of the things they were really proud of is, and you can write your own functions. There's 26 of them. They're called FNA, FNB, FNC. So this was a kind of like glass half full, glass half empty. I mean, you could write your own functions, but they don't look like the functions that are built into the language. They look a lot more obvious. Now, some of you may have read this paper, this 1997 paper, 1998 presentation by Steele called Growing a Language. How many people have either read the paper or seen the video? Okay, so the rest of you have homework. However you like to learn, whether it's paper or video, they're both excellent. The video was captured at UPSLA in 1998. But in it, Guy explores a philosophy of language design, and it makes kind of a call to action for language designers to consider growability as an axis of design in programming languages. I'm not going to read the excerpt here, but basically, he talks about when you're approaching language design, you should be thinking about how is it that the user can extend the vocabulary of the language, and how much do those extensions look like the parts of the language that are built in. And languages that are, that give more consideration to this, they're going to be less frustrating to users because they're not going to constantly be feeling like, well, the language can do this, but I can't do this. I can only approximate it. So, the view of growth, that Guy outlines is not so much about what are the kinds of things that the user code can add to a language, but how do user-added abstractions resemble the built-in language primitives? And in many ways, this paper was kind of the starting gun for Project Valhalla, because a lot of the concepts that he talked about in this paper were the ones that we started addressing many years later in Project Valhalla. So, like in many, many other ways, Guy was, well ahead of all of us. So in this talk, I'm going to explore a linguistic mechanism and a sort of language evolution philosophy for enabling language features that we add to Java to be designed with greater extensibility in mind. And as always, some people are going to say, oh, that goes too far. And others are going to say, oh, that doesn't go far enough. And that's how we know we're kind of just right in the middle. So two examples from Java's past that directly embrace the notion of growability, are the for each loop and the try with resources construct. And I think it's educational to look at how they were more and less successful and what we can learn from them and what more we have to add to the language to do more of this sort of thing. So the for each loop feature it was really interesting because it was a language feature with a library component. There was a library class, Java Lang iterable, that if you extended this class, you would be able to interact with this feature in a way that looked like it was built in. So if you have a for each loop for elements E : elements, if the aggregate on the right side, elements, implements the class Java Lang iterable, then the language, the compiler is going to desugar that loop into something that basically gets an iterator and iterates through the elements and binds the induction variable to the current element. And then we went, having done the language feature this way, we went and retrofitted a bunch of classes to implement iterable, and a lot of classes outside of the JDK did the same, which was really cool. And you could imagine, like, if you were in the room at the time when that feature was being designed, somebody surely would have said, well, why don't we just do this for list and map and set, right? Because those are the ones people want to iterate over. And that might have been a compelling argument in the language design discussions, for Java 5. And I'm really glad that they didn't make that choice. I'm really glad that somebody stood up and said, no, it's really important for classes other than these few magic classes to be able to participate in it. It's really important to not have to have an enumerated list of, here are the classes that can participate in this construct built into the JLS, and then every time we want to add something new to that list, we have to amend the language spec, right? So this was a feature that had growability in mind, and it's been very effective. Like, how many people here have implemented a class that implements Java Lang iterable, right? It was easy. You did it. You didn't think about it. It worked the way you wanted. Everyone's happy, right? A similar example that came in Java 7 was try with resources, and basically it played the same trick. So the idea is inside a try with resources block, you acquire a resource in the the block header. You do a bunch of stuff with that resource, and then it automatically closes the resource, so you don't have to remember to do it yourself in a finally block. And that's really nice. And just like iterable, it came paired with an interface auto-closable that you could implement and get the same benefit. In hindsight, this one feels less growable than iterable did. It's very much focused on a particular kind of resource acquisition, not accidentally. I'm sure there was a deliberate discussion to keep the scope narrow, and that's fine. But when you look at these two features side by side, you say, here's two features designed for growability. They both use the same mechanism for growability, but one was more growable than the other for whatever reason. And what we can learn from that is it's not enough to just anticipate growth and plan for growth. You want to go through an exercise of imagination of what are the kinds of things that people might want to do with it, and sometimes you have to use more imagination than than other times to anticipate what people might want to do with this feature. And I think while it's really cool to have features that are designed for growth, we should also keep in mind that designing a feature for growability is probably harder than designing a more closed feature. But on the other hand, the payoff is bigger. So I want to give a couple of examples of features that have been bothering me for the last probably 5 to 10 years, of features that I want to have in the language, but that I wasn't satisfied to just add them in a closed way because they wanted to be more growable. Now, these are meant as motivational examples, so those of you watching on YouTube, these are not features that we're planning to deliver immediately. They're more motivational examples for why this, this work has been done. So, as an example, let's take let's take one of the things that comes out of Project Valhalla. So Valhalla promises to make it easier to write numeric classes that are going to have the runtime behavior of primitives. And Joe's going to talk later this week about the work that he's been doing on 16-bit floating point numbers as an example of the kind of thing that Valhalla is intended to enable, both within the JDK and outside the JDK. Now, numbers are weird and interesting, and they don't exist in a vacuum. They have relationships with other kinds of numbers. So, if you have floats, we can widen them to doubles. If we have ints, we can widen them, to long and to double without loss. And in some contexts in the language, it just automatically does that. If you're going to assign, to a long and you provide an int, the language says, "Oh, I know what you mean. I'll just do it." So obviously, if someone is going to add a 16-bit floating point number, we'd like to have the same benefits. We'd like to be able to easily convert it to a float or a double, or convert a byte to a float 16. And we could do that. We could add a 2 float and a 2 double method, but that kind of falls afoul of the growability, that Guy was talking about, because it looks different than the built-in features of the language. Converting from float to double would look different than converting from float 16 to float, and that's not the kind of growability that Guy was talking about. So in the JLS, in chapter 5, there's a whole extensive section on conversions, different kinds of conversions, widening, narrowing, boxing, et cetera, and different contexts in which we were willing to do different kinds of conversions, assignment, casting, method invocation. And in the language of JLS chapter 5, it should be easy to define an exact widening conversion from float 16 to float. And wouldn't it be nice if all the other places that the language says you can use an exact widening conversion here just automatically applied? That would be cool. A related feature, also using the same example, is boy, it would be really nice if you could add 2 float 16s together with plus and not with a dot plus b or float 16 dot add a comma b. Again, that would be a way in which float 16 would not look like the built-in floating point abstractions in the language. On the other hand, operator overloading has something that's been attempted by a few languages and is somewhat of a linguistic minefield that a number of languages have hatched various flavors of disasters with operator overloading, and so it's not a topic that we take lightly. But a really useful observation that someone made recently is the big problem with operator overloading is not the operator part; it's the overloading part, right? One of people's biggest complaints about the way operator overloading is used in C++ is that we use the same operator to mean completely different things in different domains, like using the shift operator, for I/O. And that's really overloading. That's a very different thing than all of these numbers support plus, and it's the same numeric plus that we learned about in elementary school. So 2 more motivating examples, and then I'll talk some language mechanics. One of the features that was proposed in Project Coin in Java 7 was collection literals. And this is this would have been a very popular feature. I totally understand why people want it, where you can have some sort of syntax like for lists and sets and maps, like in this example, where you can say bracket string A comma string B, and use that as something as a literal for a list of string. We have something a little bit like that using libraries, where you can say list of ... which is one of those glass half full, glass half empty things. A lot of languages have built-in structural types. They have built-in types for sequences and maps, and languages like that almost always have a collection literal feature. And it's really nice to work with, right? If you've worked with this in a language that provides collection literals, you probably miss it in Java, and we do too. The proposal that was made in the Java 7 timeframe was, in my opinion, terrible. And it was terrible in multiple ways. It was not growable. It was hard-coded to support only 3 distinguished library classes: Java util list, Java util set, Java util map. And remember what I said before about what a smell it is to have a hard-coded list of classes in the language spec. But it also meant that everyone else was kind of locked out. Like if you had a collection type, or even like bitset in the JDK, it didn't get to play. If you had your own, your own list or map implementation that didn't implement Java util list or map, you didn't get to play. And so it wasn't a growable feature. And as an added bonus, which is probably not a word, it was like the most syntactically irresponsible proposal I'd ever seen, because it burned all the available delimiters on what was honestly a pretty minor feature. So thank God we didn't accept that proposal, but the motivation for that proposal has sort of gnawed at me for all of that time, and we'd like to have that. We'd like to be able to have any class say, yes, I can be the target of a sequence-shaped collection, and have the compiler just do what needs to be done. So last motivational example is object creation expression. So when we write a class, we very often, there's some distinguished instance of that class, like an empty array list, or a default value, or the 0 value for a numeric type. And we have many idioms in Java for representing this. Maybe you have a public static final field called instance in capital letters. Maybe you have a no-arg constructor. Maybe you have a no-arg factory like optional.empty. These are all totally reasonable ways to express, give me a default instance, give me a distinguished instance. But they're ad hoc. They're just conventions. They only work when a human reads the Java doc, says, oh, that's how I get one of these, and writes the code to do that. Or it means we can't abstract over classes that have this behavior. But this is a really nice behavior that we might want to reflect in the type system of a class that can provide a default instance. And we have no way in the Java language to do that. And so this is a type of abstraction that Java is not good at. Well, I hate it when Java's not good at things. So, in addition to all the obvious, the obvious reasons why we would want to be able to do this, it's just irksome that we can't. So, it's very reasonable to say, well, okay, well, the iterable trick was pretty good. Why don't we try that again? And for some of these examples, we might be able to get away with the iterable trick. Where we used a distinguished interface as our, interface, to growability. But it runs out of gas. So let's take the conversions example, right? So we could easily write an interface called convertible to, and we could say integer implements convertible to long. Great, what's the problem? Well, what about short? Short's convertible to int, and to long, and to double. But in Java, for very good reasons, you can only implement one parameterization of the interface. And that's not just a silly limitation, it's what makes type inference work. So the fact that you can only say, if I implement foo of t, I can't implement some other foo of u, that's, there's a good reason for that. So, so for things where we might want to support multiple instantiations of a relation, interfaces won't let us do that. Another reason why the interfaces trick eventually falls apart is that interfaces define instance behavior. They don't define class behavior. And that's fine if we're talking about a, something where we already have an instance in hand, like I'm converting an int to a long. Well, I have an int that I want to convert. So great, I can say convert yourself to long. But if we want to say add up a list of numbers, well, when you add up a list of numbers, you need a value to start with, a zero value, depending on what your domain is. Zero for integers, empty string for strings, etc. And if you want to add up a list of numbers, and that list might be empty, you can't ask one of them, well, what's your zero value? Because you don't have a starting value to ask. So there's a chicken and egg problem for some kind of abstractions that we would want to make, for which interfaces are just not suitable. Well, they are suitable, but not in the way we usually use them. And then a third reason why interfaces are tricky is, how many people here have read Effective Java? I'm sure everybody should have read Effective Java. But the first 47 chapters of Effective Java are about how hard it is to write an equals method. Not the first 47, but there are several chapters. And writing an equals method is hard because the equals method is asymmetric. It's an instance method on some object that says, are you equal to that thing? And if you have, that means I have two ways to ask, are A and B equal? A dot equals B, B dot equals A. And I really hope they both give me the same answer, but they don't always, right? So one of the problems with instance methods is they're not necessarily able to give you as canonical an answer as a static method is. Similarly, if I have two references that are both null, I can't ask either of them, are you dot equals to this other thing, even though they represent the same, the same reference value. So instance methods are, have some limitations that we're sometimes somewhat blind to. So, but let's talk about what's great about interfaces, because interfaces are the cornerstone of abstraction in Java. What they do is they take a set of named behaviors and they group them together into a named bundle. And that's important. Names matter, right? Java is primarily a nominal language for good reason. They allow a class to say, I conform to this bundle of behaviors. They allow the compiler to type check, do you really conform to that bundle of behaviors? You say so, but I'm gonna verify it. And then that conformance is reflected in the type system. So you can use that interface name as a generic type bound, or as a method parameter type, or method return type. So interfaces are great, but they do have some limitations that we just talked about. And the way I would describe all of those limitations is they're designed to abstract over the behavior of instances of a class, not of the type itself. And that doesn't matter if you already have an instance in hand, but if you don't have an instance in hand, it's a big difference. Another limitation of interfaces is they can only be claimed by the class itself. So an integer can say, integer implements comparable of integer. But external code can't say, hey, you know that class over there, integer, it implements comparable too, I promise, trust me. We don't have a way to express that in the language. And this is sometimes given the name the expression problem, which was coined by Phil Wadler. It's also sometimes called the inability to do retroactive modeling. In the case of integer and comparable, it's not a problem because they're both in the same module. It's easy for integer to implement comparable. But when new operations come along that are not in the Java-based module, we're unable to to reflect that, yes, I know this thing about integers in a first-class way. And then the last challenge of interfaces comes from their nominality. They have names, and the methods have names, and sometimes those names make more sense in the declaration of the interface than they do in some class that implements that interface. And sometimes those names are actually used for something else in a class, and then you just can't implement that interface. And sometimes that happens in a very accidental way, where an interface has an int-bearing method called size, but your size method returns long. Oh, sorry, can't implement that interface. Sucks to be you. As a motivating example, because this shows up with one of our motivational examples, let's talk about identifying that a class is summable. This is an algebraic structure that mathematicians call a monoid, that it has a zero value and it has an associative, that zero value is an identity for an associative plus operation. So we can model this with a Java interface, monoid of t. There's a t-bearing value for 0. There's a t-bearing value for plus, and add some other thing. And some classes in the JDK that are obviously summable are integer and string. But this interface is kind of useless. I can't make string implement monoid of string. Well, I can, but I can't use it effectively. Because I have the chicken and egg problem of, in order to start concatenating strings, I need to start with an empty string. And so I want to call the zero value, ask for the zero value of the monoid. So I have to ask an instance of string. And I don't have an instance of string yet to ask, so I'm kind of stuck. And so this is the kind of abstraction over types that we want to be able to do, but this is not a useful way to do it. This might seem like a sensible way to do it at first, because it's kind of the tool we have, right? When you have a hammer, everything looks like a nail. When you have interfaces, every abstraction problem looks like something implements some interface. But instance methods are inherently asymmetric. The receiver is treated differently than the other arguments. Having two ways to ask the same question means you could get two different answers. Object has taught us that. And also that it's easy to accidentally undermine desirable algebraic properties. So what we really want, and it's hard to see because Java doesn't let you do this, and so you often aren't able to see the solutions that you can't implement, is we want operations like plus and zero to be operations on the type integer, not on instances of integer. So the obvious thing to do there is, well, let's just make them static methods, and that sucks for its own whole set of reasons. So we're not going to do that. But as an example of the sort of thinking that led to the solution we're going to discuss, we can sort of see shades of this in some classes that are already in the JDK. So we have two classes in the JDK that kind of do the same thing, two interfaces, comparator and comparable. And comparable defines, hey, you, compare yourself to him. Whereas comparator says, here's two instances, compare them and tell me how they compare. And we use them both in the JDK. So comparable describes an inherent property of a class. Integer implements comparable integer. And there's only one way to compare integers under that, comparison metric. A comparator can be defined from the outside. I can define a comparator for integers that's not the standard ordering. Any class can do that. I can define 37 of them and use the one of my choice when I'm sorting a list of integers. And that's kind of the property, that comparator property is the property we're going after, which is I'm capturing a relation between types, or a relation on types, and I want to be able to do it from outside of the type and treat it as treat this object as the representation of this is the kind of comparison I want. And for the remainder of this talk, I'm going to describe a comparator, an instance of comparator as a witness. It is a witness to the comparability of integers, which is to say not only you can use it to compare things, but it also means it carries the knowledge of, yes, I know how to compare integers. And that's a really useful concept, and we'll see how that works in a second. But having both comparable and comparator, there's a reason we have both, because each plays a role that the other doesn't play. But having two is also a little bit of a mess, because if you look at tree map, tree map requires that either T be comparable or that you provide a comparator to the, to the constructor. And it says that right there in the Java doc. And there's a dynamic check that, that makes sure that's the case. And you know what there isn't? Static type checking. There's nothing that says, hey, you're making a tree map out of something that I don't know how to compare, and telling you that at compile time rather than waiting till your program fails at runtime. So, we like static checking. We like to be able to move error checking, as early as possible to find bugs earlier. And so, we have, but the fact that we have comparator and comparable kind of illustrates, well, we already have multiple ways to do this, and neither of them are perfect, right? And you just heard me talk about how static methods suck, but also instance methods suck in their own ways. And so, is there something else in there? Is there a best of both worlds that we can extract from this? So what I claim, without evidence, is to get the best of both of these worlds, we need something that is similar but not exactly the same thing as interfaces, where we want to do all the things interfaces do. Take a set of named behaviors and group them into a named bundle that you can claim that this type conforms to, or this group of types conforms to, and allows the compiler to type check that, but have these behaviors be behaviors about types, not about instances of types. And so interfaces are kind of like almost what we need, and if we apply the fundamental theorem of software engineering, which is any problem is solvable with one more level of indirection, we actually have what we need. So the problem with string implements monoid of string was that instances of string was the wrong place to put the behavior. The right place to put the behavior was right, but we'd put it in the wrong place. The right place is to put it on some other object that captures the notion of monoid of string, a witness to monoid of string. And then we want to make it easy, of course, for string to say, oh yeah, I have a monoid. Here, in fact, like integer, I have two monoids, addition and multiplication. And also make it easy for for both humans and for compilers to say, okay, get me a witness to monoid of string. All right, get me the way that I add up strings through concatenation. And this extra level of indirection hopefully will solve our chicken and egg problem and some of the other problems that interfaces have, like the lack of retroactive modeling or nominal indirection. Okay, so how do other languages do this? Many other languages have struggled with this very same problem. So in functional languages, Haskell especially, there's a notion called type classes, which are almost like Java interfaces, except that they abstract over types and not over the behavior of the types. Scala has a sort of more fine-grained, do-it-yourself type-level behavior construction kit called implicit parameters that can solve a lot of the same problems. C# and Kotlin are both going through their own set of explorations of this. I think the latest name for the C# version is shapes and extensions. They've changed the name several times. A couple other languages have a notion of protocols that can be defined externally to the to the definition of a type. And all of these are sort of dancing around the same basic puzzle, which is, how do I abstract over the behavior of types without it being part of the definition of a type? I could go through all of the mechanics of each of these, but I won't. I could go through the pros and cons of each of these, but I won't. I'm going to cut to the chase and say the one that we found most appealing was the Haskell model of type classes, and what we're going to propose here is most similar to that. But if you look at all these features from like a 30,000-foot view, what you see is kind of like the same feature with two knobs. And those two knobs are who can publish witnesses, and how do we find those witnesses? And the rest of it is mostly mechanics and syntax. So we probably won't call it type classes in the long run, but that's the name that it has, that most people understand as. How many people here have used type classes in Haskell, just out of curiosity? Okay, so some of you are familiar with what I'm talking about. Hopefully for the rest of you, it will become clear soon enough. So I'm going to say that a type class is just, in Java, is just an ordinary interface that defines the behavior of a type. So it's probably parameterized by some type. It's not necessarily meant to be implemented by the type. It's more like comparator than like comparable. So the type class flavor of monoid is a little bit different from the interface example I showed you a few minutes ago, because the addition method takes two things to be added up. So this interface monoid of t that has a t-bearing 0 method and a plus method that takes two t's and returns a t, that is a good example of a type class that represents this type can be added up. And we have some interfaces like this in the JDK already. So I'll further define a witness to some parameterization of a type class is just an ordinary instance of that interface. And we write APIs today that consume witnesses, we just haven't been calling them witnesses, right? So if I have a sort method that takes a list of T and a comparator of T, we can think of that comparator as a witness to the comparability of T. And we have lots of methods like this in the JDK. We write them every day. So far, I haven't done anything, have I? Right? It's like we could do all this in Java 5. There's nothing interesting here. This is just using concepts that are already in the language, but giving them new names. So what's missing to actually use this for the kind of abstraction that we'd like to use it for? How do we publish a witness to a parameterization of a type class? And how do we find a witness to a parameterization of a type class? And that will require some new language feature, but hopefully we can piggyback that onto things that are already in the language. And some constraints and goals that have already come up in the examples that I've given, we want to be able to say there should be it should be possible to express multiple witnesses to some behavior that involve the same type. Short can be converted to long, and to int, and to double. And we'd also like to be able to derive witnesses from other witnesses. So, for example, if I have a witness to monoid of T, T's can be added up, I should be able to mechanically derive a witness to monoid of optional T. I should be able to add up optionals by unboxing the thing, adding it, and boxing it back up. And I shouldn't have to declare witnesses to optional string and optional integer separately. I should be able to just derive one from the other. So these are things that we would like the mechanism to be able to do. And clients need to be able to summon the witness. They need to be able to say, give me the witness of comparator of string. And the way I'm proposing we'll do that is with some kind of witness literal where you name the type that you're witnessing, comparator of string, dot witness, straw man syntax. And so then you can just summon a witness by uttering its type. Right? So if we want to sort a list of strings, you say sort strings, comma, comparator of string dot witness. Now, you haven't said what ordering you want. You're saying, I want the canonical ordering that strings are ordered by, that hopefully someone else provided, and if we can't find it, I'll get a compilation error. Now, people look at this code and they immediately see glass half full, glass half empty. On the one hand, it's more abstract, it's more loosely coupled. I haven't had to go read the Java doc and say, what's the name for the comparator that compares string in the standard order? So that's nice. I don't have to know where that witness comes from. On the other hand, a lot of people would say, why do I even need to say that thing at all? Why can't I just say, sort the strings and have the language figure out? So we'll explore some ways later on how to reduce the emptiness of the part of the glass that's half empty. But for the time being, let's focus on the part that's half full. And like I said before, different languages that have similar features, they vary. One of the ways in which they vary is who can declare witnesses, how do I find the witnesses, how do I resolve them? And in this design, we've chosen a somewhat stringent constraint that some people will absolutely hate, which is that the parameterization for a witness be well-defined. That when I say, give me a witness to comparator of string, I'm asking a well-defined question, that there be one. I don't want, when I say, give me a witness to comparator of string, to get a different answer than when you ask, give me a witness to comparator of string. And there's a reason for that besides just predictability. So we would like for all queries for a given parameterization to always come back with the same answer, no matter when you're asking, no matter who you're asking. And what that means is that witnesses are basically symbolic constants. And we all know how much the JVM loves to grind symbolic constants. So not all languages were brave enough or stupid enough to adopt this constraint, depending on how you look at it. It's certainly convenient to be able to say, when I say comparator of string, I mean this. And some languages let you do that. So like Scala has this incredibly complicated lookup procedure for implicits where it will look in the local scope and in the imports and in companion objects and under the couch and in the back of the freezer and in Grandpa's World War II uniform. And that's great for flexibility, very not great for being able to look at code and know what it says. So the people, I'll just characterize, the people who are going to hate this proposal are the same people that hate that Java doesn't have extension methods for exactly the same reason. It's the exact same philosophy that led us to default methods and not extension methods that lead us to this constraint. But if you like optimization, how many people here in this room like optimization? So if you like optimization, the fact that witnesses are symbolic constants means that they are much more amenable to inlining and intrinsification and having things boil down to the handwritten machine code you would have written if you could. So, okay, so what does this look like? Supposing integer wants to declare a witness to comparator of integer. What we would do today is we would pick some name like comparator and say public static final comparator of integer, comparator equals blah, and we rely on humans looking that up via the Java doc. So to make this findable as a witness, we can just mark it as a witness. It's still a field. You can use it as a field if you want. The code that uses it as a field can keep doing so. But it also means that integer is proposing this value be used in the search for a witness to comparator of integer. And if you have a more complex witness, like I gave the example of wanting to derive a witness to monoid of box of t given a monoid, a witness to monoid of t, well, what would we do today? We'd write a simple method that lifts it. It takes the witness to monoid of t, and it defines a new monoid on box of t, and what does it do? Well, the 0 value is just put 0 in a box. And the plus operation is unbox the values, plus them together with the monoid that you've been handed, and rebox the result, right? We write code like this, maybe not all the time. We should write code like this all the time. But we can write code like this today. And similar to the previous slide, we can mark this method as here is a rule by which you can derive witnesses from other witnesses. And this proposes a mapping from witness to monoid of t to witness of monoid of box of t that can be used in the witness search. So one of the reasons why it took so long from the time I started thinking about this feature to the time I'm giving this talk is the previous 17 iterations of these ideas were much less intrusive. They define many more new linguistic concepts. But here, we're leaning on concepts the language already has. We're leaning on interfaces. We're leaning on instances of interfaces. We're leaning on fields. We're leaning on methods. And so we've kind of distilled it down to something that fits into Java much more cleanly than some of our previous ideas. Okay, so that's half the problem. How do I declare a witness? The other half of the problem is how do I find a witness? If you have a type theory background, you can think of the witness fields and methods that I just described as axioms and rules in sequent calculus, where you have preconditions on the top of the bar, and then a bar, and then a conclusion on the bottom of the bar that you can, you can derive from that. Or if you're familiar with Prolog, you can you can think of it as a set of facts and inference rules in a Prolog program. But however you think about it, deriving a witness is basically a proof search, where you say, gee, I have this witness field, and I have this witness method that turns this witness into this other witness, and it's going to it's going to do a search for a tree that says whose leaves are either witness fields or no-arg witness methods, and whose intermediate nodes are other witness methods that produces a witness of the right type. And we have a prototype of this. It actually works pretty nicely. And to preserve that goal of well-definedness, this is the part people don't like, we only consider witnesses proposed by the classes that are actually involved in the witness you're looking for. So if you're looking for a witness to monoid of box of t, I'm going to ask monoid, I'm going to ask box, I'm going to ask monoid box of string, I'm going to ask string, I'm not going to ask integer. I'm not going to ask Uncle Bob. I'm just going to ask the types that are named in that type. And of course, there's some rules for what if they both have an opinion? How do we resolve conflicts? But this is what's going to give us that well-definedness that we're looking for. So the conflict resolution rules are actually pretty simple. They are kind of inspired by other rules that are already in the language if you kind of squint and tilt your head a little bit. So when we're looking for monoid a box of string, we're going to take string's opinion over box. We're going to take box's opinion over monoid. And you can think of that as monoid might have a general opinion, and box might override that opinion, and string might override that opinion further. And that way, abstract classes can provide general rules. So like comparator can say, well, if t is comparable, then I can give you a comparator for t. But I can't say anything else about, about other types. And then other types could have a more refined opinion about how to compare them. Similarly, one of the things that, that type classes can do is that they can abstract over multiple type variables. I can convert integer to long. And in such a situation, it's possible that both of the types involved might have an opinion. Integer might have an opinion on how to convert to long. Long might have an opinion about how to be converted from integer. And so if, and they're kind of at the same level in the tree, so one doesn't have priority over the other, but because a witness is a proof tree, and we can compare proof trees structurally, it's perfectly fine if integer and long both have an opinion, if it's the same opinion, and we have a well-defined way to say, is it the same opinion? Do they have the same proof tree? So, all right, that's some cool language mechanics, but what does it gain us? Well, so part of it is the ability to do some retroactive modeling. If I have to say integer implements comparable of integer, that means that old classes can't implement new behaviors. And what I mean by new is that it's not in the modular dependency of the class that, that we're looking at. So I can say integer implements comparable because they're in the same module, or if comparable was in integers modular dependencies, of which there are none other than the base module. So that's a pretty big constraint for, for fundamental classes like integer and string, which are often the classes that we would like to add new behaviors to. So if some other module added a new behavior, like let's call it formatable, we can't make integer implement formatable. And like I said, that's what is called the expression problem. But we can provide a witness to formatable of integer. And so if we define these type behaviors with type classes rather than by extension, then we can add new witnesses. And formatable can say, I know about integer because it's in my modular dependencies, and I have witnesses to formatable of integer and formatable of string and such. Separating the witness out with with a layer of indirection also addresses the problem of names, right? So a good example of the nominal indirection problem is autoclosable. The release method in autoclosable is called close, which makes perfect sense if your resource is a file handle. But if your resource is a lock or a semaphore permit, well, you are releasing it, but you're not closing it. And unfortunately, when we design interfaces, we have to give them names that have to be good enough not only for the name, but for every foreseeable class that might ever want to implement that interface. Whereas with some indirection, all we have to do is say, well, here's how we implement releasable of lock. And we don't have to worry about name clashes between releasable and lock. So you would be completely forgiven if you listened to all of this and said, oh, this is about better generics, right? In fact, that's kind of the obvious answer, because that's what every other language uses this mechanism for. And yes, it would be great to be able to use this to write better generics, like the sort method is generic in T, and it requires a witness to comparator of T, and have the runtime automatically provide that, that witness. And unfortunately, it's not a great fit for the generics we have, because in order to be able to do that, we need one of two things. We either need reified generics, so that when we actually get into the implementation of the sort method, it can say, now give me the witness to the whatever T you've passed me. Or we need to somehow arrange for the witness to be passed in as some kind of parameter, which is what Scala does with implicits. Implicits seem kind of easy, until you think about the lifetime of code, over time, of how's this code going to evolve, and what and how does it interact with overload selection and binary compatibility and all of that. So a lot of the ways in which we might want to use type classes for building better libraries are going to run into the wall of erasure before they really get off the ground. So, well, that's really depressing, Brian. Why did you tell us about this when we can't use it? Well, it's not just about better generics. It's about growing the language. And so while the features I've described so far may not yet be enough to write the richer libraries that we can easily imagine being able to write with them, they are kind of exactly what we need to write more growable language features of the kind that I talked about earlier in this talk. Because we can define language features in terms of, if I had a witness to this, then I would be happy to use this type in this way. So let's run through our examples, our opportunity for growth examples, and see how we might address them using type classes. So how many people here have read Chapter 5 of the JLS? So the experience of everybody who reads Chapter 5 of the JLS says, okay, that was really obvious. I guess I didn't need to read that. Which is to say that it has a lot of words about what can be converted to what that kind of almost perfectly matches your intuition for just do the right thing, please. And so the fact that so many of us can program in Java without having to have read it, that's winning. But if you were to read it, you would discover that there are many kinds of conversions. There are many contexts in which some conversions are allowed in this context, but not that context. And when it comes to the primitive types, it has these big, nasty tables, 9x9 tables of what kind of conversions are permitted between what kinds of types. And we would like for value types to be able to participate in this scheme. We would like to be able to do that without having to amend Chapter 5 of the JLS every time we come up with a cool new numeric type. In fact, we'd like to get rid of this horrible specification in Chapter 5 and replace it with something that we can derive from the properties of the types that are convertible. So as an example, supposing we want to model the relationship of exact primitive and widening conversion. So integer to long is an exact primitive widening conversion. That means I can widen integer to long with no loss of information. I can go back to integer and I get back the same integer I started with. It's not going to throw. It's going to convert on every integer. There's no exclusions and there's no loss. So I can model this type relationship with hopefully a better named interface than the one that's on this slide that says, okay, I've got two types and one of them I can widen to the other and then I can narrow in the opposite direction. And then types like short can say, I've got a witness to that horribly named interface relating short to integer and short to long and short to float. And new types, whether they're in the JDK or not, could also witness exact primitive widening narrowing, like float 16 to float 16 to double. And then we could replace that nasty table, illustrated here, with a rule that says, well, a value class T can be widened to a value class U if I can find a witness to exact primitive widening and narrowing from T to U. And then this would flow into all the places in the language where we use primitive widening. So that would be nice. It both makes the definition of the language clearer, but it means that conversions that are added by libraries are treated exactly the same way as conversions that are built into the language, which is what Guy was talking about in growing a language. We can play a similar game with operators, so just assume that I've already reiterated what a minefield operator overloading is. We've been thinking a lot about how do we limit the worst abuses of operator overloading, and there are kind of four things that we think we can do to make operator overloading a little bit less of an attractive nuisance. One is kind of obvious: no new operators. Java has the operators it has, they have the syntax they have the arity they have the associativity and precedence that they have that's written in the JLS, and that's not going to change. So no new operators, no weird strings of symbols, sorry Haskell. Operator overloading is for value types. Some people will be disappointed at this. But why are we even considering operator overloading? We're considering operator overloading because we want to be able to express numerical calculations in a way that look like mathematical calculations. And why does Java have a special operator for plus and not just a method called plus? Because numbers are special. And so it seems reasonable, even though people are very creative in thinking of new things they can do with operators that, on things that are not values, it seems reasonable to restrict operator overloading to values only, and particularly to numeric values, because the operators that we're overloading have numeric meaning. And when I say numeric meaning, I mean like the meaning derived from algebraic structures like monoids and groups and rings and fields. So the notion of addition doesn't exist. It didn't get pulled out of a hat. It's mathematicians have studied algebraic structures with addition for a long time, and we have many good examples of how to describe its properties. And then the other is take the set of operators that make sense on integral values or floating point values and put them in one interface and say, you either implement them all or you don't implement any, because that reinforces that these operators are supposed to mean these mathematical things, not using shift to represent IO or plus to represent stick an element in a list. And so we think that if we do that, we can define our interfaces for operators. We can say float 16 has a witness to the floating point operators and the comparison operators, and then the language can translate it appropriately. So how does that work? So if the compiler encounters an addition of C equals A plus B, where A, B, and C are float 16, the language is going to say, okay, well, can I find a witness to the arithmetic operations on float 16? Well, that's something it can verify statically at compile time. And if it finds it, it can summon the symbolic constant for that witness and translate this as a load up the witness, call the plus method on it, and that's the result. And that's pretty cool. It probably looks a little slow, when you look at it at first, say, gee, that seems like it might be a little slow, but this is where we come back to witnesses or constants. And so that witness literal is an LDC of some constant defined by constant dynamic. The JIT knows that the methods on that constant object are monomorphic and will be very willing to inline through those and then discover, oh, I have an intrinsic for float 16 dot plus. That's going to boil down to this operation in this Intel instruction set, and we're going to end up with a single instruction out of that. And so there will be a Conde bootstrap that reifies the proof tree that the compiler found at compile time that says, well, to get the witness to this, first get this witness field and then call this witness method on it and install that as a constant in the constant pool. So the trade-off that we made here is we've made witness resolution less flexible in exchange for delivering in not only more clarity and visibility, but also better performance in the cases that we think are really important. So what about collection expressions? I didn't like the original collection literals proposal. What's a proposal I might like? Well, there's a lot of ways you might define an interface that for building a sequence-like structure. One of them might be, give me a builder for a list of strings of size 3, and then I'm going to pass you 3 strings. And there's other ways to define that witness. There's a significant API design exercise buried in this language design feature. And then we would provide witnesses, for sequence buildable of list of T and array of T and bit set and things like that. And then when we encounter a sequence literal, like this one for bit set, we're going to say, okay, well, summon the witness of the sequence buildable, ask for a builder of, with 3 slots, and then pass in 1, 2, and 3, and okay, now build it. And again, this may look, gee, that might be inefficient, but because everything here is a constant, I think the VM might be able to chew that up a little bit more effectively than it looks like. And if you want to write a new class that can be expressed as a sequential list of things, you just provide a witness to sequence buildable of my class, and the compiler will do the extra work for you. So this is obviously not a complete feature. This is at the why don't you just level of specification, but it seems like a viable path to get there. In the way that the proposal back in the Java 7 days was not a viable path to get there. And then the last one, the last example I talked about was distinguished creational expressions. It's something we've run across in Project Valhalla, where some value types have a natural default. Some value types have no natural default. If I say, new foo, new null restricted foo of 10, I declare I want to get an array of those things. Well, what does array creation do today? It fills the array with default values, either zeros or nulls. And you'd like to know whether the type has a valid default. And if it doesn't have a valid default, you'd like for the compiler to say, sorry, you can't allocate the array that way. You have to allocate it some other way that's going to ensure that there are valid values in the elements. And so how would we do this? Well, one way to do it is to have some kind of supplier-like interface that represents implicitly constructible, and have certain value types can provide witnesses to I am implicitly constructible. And then the linguistic feature of new null restricted array is conditioned on, well, is there a witness to the implicit value? And this is really nice. If you followed the discussions in Project Valhalla, this is a feature that we've been kind of diffident about because we didn't want to push it into the VM. It's like extra work that we're asking the VM to do that VM shouldn't really have to do. This is a way to keep that feature in the language, but allow a given class to participate in the feature based on whether they've done some extra work or not. So it means that we get to put this behavior kind of in the right place, which is a good feeling. So I've outlined a mechanism for designing growable language features. I've talked about in very sketchy terms how we would use it for 4 potential features that have been irking us for quite a while. So this is great, right? But it's worth observing that this feature doesn't make it any easier to design these language features. In fact, it's probably harder to design a good growable feature than a good non-growable feature because it requires more imagination for how are people going to want to interact with it. On the other hand, it enables you to design better features, richer features, features that users can do more with, and ultimately, maybe we won't have to design as many language features in the future as a result. So designing a feature for growability might be harder, but it offers us a bigger payoff. And there's something nice about being able to capture optional behaviors of a type without having to have special syntax for that. You just have a way of saying, yeah, here's how I provide the behavior of comparability or default values or sequencing or what have you. So summing up, type classes is not a new concept. It's almost as old as Java. It's a well-understood abstracting mechanism that's been used in a lot of other languages, and it's very similar to something we already have, which is interfaces, but it's slightly more powerful because it's sort of like abstracting over things one level up, over the types rather than over the instances of that type. And we can add type classes to Java by adding relatively little to the language. A mechanism for publishing witnesses and a mechanism for finding witnesses that we can piggyback on existing language constructs like interfaces, fields, and methods. Hopefully in the long run, we'll be able to use this to build richer generic libraries and conditional behavior and those things as well. But in the short term, we can use this to deliver growable language features, including features people have been asking for quite a while. So with that, I think we have about 10 minutes for questions. So who has the microphone? Looks like, okay.
Okay. Yeah, thanks for the talk. So I was wondering, on all of this kind of design process, what's the role of like what other languages in the JVM are doing right now? Because like you said, Scala has their own way to do this, especially for things like just the default instance. Every language seems to roll their own. And how do you make sure that this doesn't add yet another, like the typical edge case you did, yet another standard way, so that then all other languages are kind of forced to comply with the Java rules in this case?
Yeah, even though this is the JVM Language Summit, it's not actually a JVM feature, it's a language feature. It's built on JVM features like constant dynamic, but it's a feature of the Java language that other languages are free to emulate or not. Now, some languages on the JVM, like Kotlin, are very interested in interoperating with Java code, and so they're going to have to figure out what their interop story is. But other languages, they're just their own little world, and they can, use, like there'll be Conda bootstraps that they can reuse, just like other languages reuse the Lambda bootstraps. But I think it's largely independent. Except for the interop story. And then the interop story is going to be different for each language, because each language has had its own way to solve this, and they get to decide how they want to interoperate with what Java has done here.
Yeah, thanks. I really enjoyed this talk. I've written a lot of Haskell in my day, so I see a lot of the value coming through here. So this is sort of like on the Java side, sort of a paradigm shift in the Thomas Kuhn kind of sense. I think we've been focusing really on this edge case for a while about where this pain point is and trying to negotiate a way through it. And I think this is a really big proposal packaged in a fairly small syntactic and syntactic change.
Don't tell them.
Okay, fine. I think the big implication here is thinking about how people think about Java, because classes and objects up to this point have sort of traveled as kind of a unitype in some ways. Like some folks have considered it a unitype. Some folks consider named nominal classes as nominal types in the sort of a la Haskell sense. And this kind of is committing Java into that latter category a little harder, finally taking a position that, yes, we're going to start reasoning about types more directly. So for instance, in the example with the generics, the generic parameters, you have parameterized types, and you say box T, if something is a witness to box T, let's say, and I haven't had enough coffee to fully articulate this, so bear with me, but if something's a witness to box T, it could also witness optional box T. What's sort of went unmentioned there maybe is that we need to have like fully applied types in this case. Like T has to be there. You can't have a raw type. And so I guess I feel like the community's ready for this, but I guess how much have you thought about how this may impact the way we reason about things, and how it may, I think it also will open up future opportunities also in things like algebraic data types and things like better parsers and stuff like this. So you can speak to some of that.
Yeah, so the good news is, we have an initial target here that is something people can use that without having to fully reason about all the mechanics of it, right? That when we get to the part where, yes, this is about writing richer generics with complex dependencies and conditional methods and all that, then yes, people are going to have to internalize the fact that the type system got richer. In the short term, I hope, a lot of people will just say, oh, I can use plus on float 16. Oh, I can finally have collection literals for a list of string. And a lot of people will just be happy to use the features that this enables and the libraries that this enables. And so I think we have some time to get there. But you're right. We're raising the bar, and some people will cheer and say, "Yeah, but you're not raising it enough." And some people will say, "Why do you keep making Java more complicated?" And we have to find that balance.
Okay, obviously I want to use exactly this at runtime.
So you want to look up witnesses at runtime?
Yes.
Yes. So If your question is, can you? The answer is yes. There'll be a reflection mechanism where you, just like you can reflectively load a class, you can say, can you reflectively find a witness to this Java lang reflect type? And it will emulate the lookup procedure in dynamic reflective code and take a little bit longer and say, here's your witness.
Yes, the question is, usually you will do a lookup on a parameterized type, and at runtime you have erasure, so you don't have it.
Yeah, so the interaction with erasure here is, since things are going to get erased before runtime, you need to arrange to put the witness somewhere where it can be found, right? So we do our witness lookup at compile time. We build a proof tree that says, to construct this witness, I take this field, feed it to this method, then feed it to that method, and there's my witness. And then we reify the proof tree as the static argument list of a condy. So you can LDC that witness, and at linkage time, it will fetch the field, invoke the methods, and then you get a symbolic constant out of that.
Okay, so is it based on Babylon?
Based on what?
Babylon.
No. It's
because you do exactly the same thing.
So I'm sure Babylon will be interested in this, but we don't need Babylon in order to do this.
Yeah, hello. Thanks for the talk. I wonder if you can repeat how resolution works for finding witnesses. For instance, with collection literals, the original example is more or less clear, but what happens, for instance, when we pass a collection literal as an argument to a method, and there's a few overloads and a few witnesses and so on?
Yeah, okay, so that's a great question, which has to do with what's the interaction between witness resolution, type inference, and overload selection. And this is a monster that we confronted in the Lambda days, because Lambda is based on target typing. And if you have overloads where you say M and then something that's Lambda shaped, and there could be two overloads, each of which represent different functional interface types, we can't strictly sequence overload selection, type inference, et cetera. We have to sort of do them together. There's a similar but familiar kind of interaction there, where if you're passing, say, a collection literal to a method, in order to figure out what witness you need to know what is the collection type, what's the element type of the collection, and I get that from type inference, and there may be multiple overloads that I'm going to have to say, all right, is this one compatible with collection literals? Is that one not compatible? So just as we have an interaction between type inference and overload selection for lambdas, which are another kind of structural type, we would have that with collection literals, which are a structural type. So.
Speaking about implicit widening conversions, do you think it's really a good idea? Because even with a limited number of conversions between primitives we already have, I've seen a lot of weird bugs, like primitive character was unexpectedly, implicitly reinterpreted as int, and good luck debugging the result. So if you have different floating point types in the same context, probably it will be better for the code to explicitly convert every time, because otherwise, who knows what will be the result. And how about admit that implicit conversions in Java is not very good thing, and not doing it even worse, allowing user-specified conversions?
So to summarize Tagir's question, boy, I don't like implicit conversions. They're confusing, they cause bugs. Why are you giving us more of them? And that's a totally valid question. And so some languages take a very extreme view of that, like Go has no implicit conversions. Everything is done with casts, except that in Go, it doesn't differentiate between exact cast and lossy cast. So almost, but like absolute failure on that part. One thing that some languages have tried to do and failed with implicit conversions is build chains of, oh, I can convert A to B and then B to C and then C to D. and then you end up with multiple possible paths. We're not going to do that. Conversions are point to point. And because they are restricted to values, I am less concerned about the kinds of things that of problems that you have than in languages that let you define implicit conversions from anything to anything. I could be wrong, but specifically with numerics, it would really suck if I said, you know, float 16f equals 0, and the compiler said, sorry, invalid program, you can't assign an int to a float 16. Or similarly, float f equals, and then a float 16, I think people would be really annoyed if they had to explicitly cast in that situation. And so I totally get how, like, if you program precisely with here are all the types of all my expressions, you get a more precise program with fewer bugs, but you also get more annoyed users. And so we're trying to find that middle ground of, for the things that, like, we know are obvious, we can do them. Now, since you mentioned implicit conversions, I will point out that it's not a bug, it's a mistake, in chapter 5 of the JLS, where we treat the conversions from int to float as a widening conversion, even though it's lossy. Now, okay, it was a long time ago, and it's easy to throw rocks, but that's not a widening conversion. That's a lossy conversion. So we're going to be fixing the spec to say that, let's say we call that a legacy widening conversion. We had much worse names for it, but I won't repeat them here. So that when we say widening, it really is an exact and reversible and lossless conversion. And I think that will make things a little bit better. That was an example, by the way, of just copying too literally from the C spec when Java was being written. There's a number of things that we said, oh, C does it this way, we'll do it this way too. And in hindsight, it would have been nice to exercise a little bit more of the kind of questioning you just asked of, is that a really good idea?
So I think Ian's exactly right. This is a bit of a paradigm shift. I was wondering if you have thoughts on the extent to which we would encourage people to adopt a different style, to which we would actually maybe go and revise existing classes throughout the platform to use witnesses. For example, one could imagine if there were a future version of effective Java that there being an item saying, don't implement an equals instance method. Instead, provide an equality witness. Don't implement a compared to instance method. Instead, provide a comparator witness. And then we back rev all existing equals and compared to methods to just go call the witnesses.
Yes, but, right? So down that path is a significant API design for equalators and two stringers and hash coders and whatever we're going to call those types. And but we certainly could do that, and I think we would encourage. I think that's already kind of captured in the effective Java advice of prefer composition to extension, right? So integer extends comparable of integer. And I think it's reasonable to view that as, yeah, but it would be better to compose the comparison function by providing a comparator witness than by extending comparable. And so we would probably not deprecate, but discourage things like comparable when they have a type class twin like comparator. How far we would go for the equals hashcode toString methods is a really good question, because one of the things that we confronted in records is, so records give you a nice equals hashcode toString derived from the state description of the record. And then if you want a slightly different hashcode, like ignoring one of the fields, you have to rewrite it from scratch.
This is much more interesting for equals compared to because they're asymmetrical. Right. Hashcode toString doesn't necessarily.
Right, but yeah, equals and compare to, you'd like for them to be consistent. You'd like to be able to describe them in one place so that you don't have two descriptions that can get out of sync. So I think it would be nice to have those. It would be nice for the language to let you use those. It would be nice to get to that vision that you described. So I have no objection. It's just more work. Okay, we have time for one more question, I guess. Lewis.
And this is a fast one. Am I audible? Possibly even a yes or no. All of your examples of witnesses are interfaces, not abstract classes or anything else. Do you imagine that as a necessary constraint?
So I think so, because I want witnesses to be symbolic constants. And abstract classes are likely to drag in state and identity and all of that. So, I mean, we could probably constrain abstract classes to, in such a way that they could be useful as witnesses, but I'm not sure it'd be worth it. Thank you, everybody.